Okay, so next up we have Teik. Teik works in the niche area of cryptographic security design and integration, having implemented numerous successful projects for banks, government agencies, and enterprises. He previously led a multi-factor authentication solutions provider, ESG, for over a decade for eventual acquisition. Teik currently runs its startup, PQC.com, focuses on providing quantum readiness solutions. He holds a bachelor and master's from National University of Singapore and a PhD from SUTD. Let's put our hands together to welcome Teik.
Thank you. And thank you for inviting me. And hello, my name is Teik Guan. So this session is going to be a bit more interactive, I hope. So I need you all to ask questions. I need you all to think about it or try certain things. If I say some rubbish thing, please stop me, say, hey, it doesn't sound correct, and please come and please have this interaction. If not, the talk will end in 10 minutes, which is not what we want to do, right? So a bit of background, I did my computer science undergrad studies in NUS, but it was even before it's called a school, it was called a department in the Faculty of Science over at S15. So the physics guys there took over the com science building. So computer science was meant to be there, and then you guys all came here. So very different. I thought com science was still there. Unfortunately, it's not the same really. So that was then. That was in the 90s, and before Y2K even. So we even did COBOL. We did a lot of other kinds of things. Django and React definitely didn't exist. JavaScript definitely didn't exist. Even web didn't exist then. But now we are in a different world and more exciting. So today's talk that I will cover is really about, I put it as knowledge sharing about post-quantum. And it's about trying to get you guys into that new wave of what quantum technology is. If you're following what Jensen Huang is already talking about since yesterday to today, it's all about quantum, right? Even NVIDIA wants to set up this whole quantum department to get into this whole what is quantum and what they can do to improve the quantum side of things. So my talk, two parts. We'll talk a bit about quantum computing. We'll give you a little idea about it. Then we go into the cyber security side where we talk about threats and the post-quantum side of it. Okay, so let's start with quantum computing. Right, so what is quantum computing? I mean, most people are starting to figure out, ask them this and that, what is a quantum computer itself? And if you try to figure it out, it really comes down to a few things. It just comes down to a couple of bits. Oops, so what we're talking about is just moving from bits to qubits. That's not quantum computer, right? So moving from bits to qubits and really about new principles inside there. So you guys learn about bits, right? Digital bit 0 to 1. And if you want to go to use a quantum computer, you are no longer programming the bits, right? You're not programming your digital bits, not flipping bits from 0 to 1, 1 to 0. You are manipulating qubits. A qubit is the basic form of how a quantum computer stores data. And it is essentially can be viewed like a 3D ball, a 3D sphere itself, right? So bit is only imagine a one-dimensional line, right? 0 and 1. A qubit is three-dimensional. It's 0 and 1, positive, negative, 0 and I being square root minus 1. And the value of a qubit is somewhere on that surface. So it's a lot of possible values that come out of it. The downside is that when you want to read this qubit, it goes back to 0, 1. Right, so that's just the thing. The qubit during computation is somewhere on that surface, and then when you read it, it tells you 0 or 1. It's not going to tell you where on the surface it is. It's a probability of how far it is from 0 and probability of how far it is from 1, and it'll give you that number 0 or 1. Right, so you have to run it many times to get a more probabilistic answer. That's really what qubit does. So what we already know, it can store more data. If you look at how much more data it can do, 1 qubit is like 2 bits. By the time you go 10 qubits, it's like 1 megabit already. So imagine you start to go 100 qubits, 1,000 qubits. You start to imagine the size of what this quantum computer can program, can really manipulate. How do you manipulate qubits? You use gates. You've learned about AND gates, OR gates, not gates, OR gates. Same. These gates exist in quantum computers. All right. what is different is that there are two additional gates that you will start to learn about. But on top of these two additional gates, nothing else. Everything is the same. You're just manipulating in gates. And with these gates, you start to have two different type of concepts. The concept of superposition, which means to say that it's somewhere on the sphere surface, somewhere between 0 and 1, as long as you haven't read it. You read it, drop to 0 and 1. The other one is entanglement. Entanglement is to say that two qubits are correlated. You modify one qubit, the guy gets modified at the same time. And because of this modification, that's how really the speed up happens, right? Because first of all, I can already process more data. Once I can process more data, I can also manipulate it such that if I just tweak one qubit, all the other qubits which are entangled to this qubit are also manipulated and correlated at the same time. Suddenly, I'm processing a lot faster. And that's really how quantum computers actually go faster. Quantum computers' clock speeds are super slow. They're not running in the gigahertz. Some are in the hundreds of tens of hertz to kilohertz, at most megahertz. No one has even reached gigahertz. So a quantum computer is actually very slow, but because it can process more data, and because data can be entangled, we can go faster. So what is Jensen 1 talking about? Jensen 1 says, hey, if I combine the CPU plus the GPU plus the QPU, which is a quantum processing unit, I suddenly can do a lot of things. Because whatever that is standard processing, I can use it on my CPU. Whatever there is more tensor calculations, I go on my GPU. Whatever there's more quantum related, I go on my QPU. And a combination of these three is what we expect to see in the coming future. What is in the coming future? Well, we are looking at the quantum computer, right? So when quantum computers start to become useful, when does that happen? Give you an example. All the Jensen Huang's biggest GPUs right now, if you go use it to simulate a quantum computer, run whatever it's trying to do, he's hitting somewhere around 60, 70 qubits. That's the power of the GPU combined across all the things. But if a quantum computer starts to go 100 qubits, 1,000 qubits, we're going to be able to solve problems that we never believe we can solve. Because this is the kind of computing and processing power that is out of this world right now. Okay, and that is what we are looking for. Countries are already spending billions. So on an average, we know that about $50 billion is put into quantum computing research. And that number is growing more and more. And hopefully within the next 5 years, we're going to see that 1,000 qubit quantum computer, and that's going to solve problems that we cannot imagine. Okay, and you need to understand what you mean by cannot imagine, right? If someone, in the past, the person who invented the microscope didn't realize that he can look at bacteria inside there, and that goes into microbiology, which is a totally different field altogether. The person inventing a microscope doesn't understand that. But with that machine, new fields are created. And this is what we are really hoping to see. That with a quantum computer solving problems that we cannot imagine right now, and in 5 years' time, that means maybe when you all just graduate, few more years you'll start to graduate, right? If we are starting to solve problems that we cannot imagine, that is what is really exciting about this whole quantum is coming. Right? So my goal today, let you understand a bit about quantum. Usually most people say, hey, how to start doing quantum programming? Go to IBM Qiskit, download and start to write Python programs. I didn't grow up learning Python, so Python didn't exist when I was doing programming, so I didn't want to use Python. I'm a C programmer, right? I still do C programming. So what we did is that we wrote a 20 qubit quantum simulator that runs on your browser itself. So if you want to run a little quantum computer on your phone itself and really simulate it, you can scan this button and scan this QR code and you can start to play with it and actually literally see some of the QR code and how it actually moves. But this is too boring. I'm going to start with a hello world. Right. So a hello world, why don't we do a hello world quantum computer, right? Right. So this is really what we call a Bell circuit. A Bell circuit is a 2 qubit quantum program, two qubits only, that puts these two qubits in what we call an entanglement state, a fully entangled state. Okay, so it starts with two gates, and I will introduce a bit. These are the new gates that you have to learn. One is this Hadamard gate, or H. This gate puts a qubit into a position halfway between 0 and 1. All right, this is the Hadamard gate. And then this is a control NOT gate. NOT gate is what it is, from 1 to 0, 0 to 1, you all know. Control NOT gate says that if the bit going in the control is 1, then the NOT is carried out. If the bit going through the control is 0, do nothing. And amazingly, if you just do the math behind it, if Hadamard gate moves a qubit 50% 0, 50% 1, and this control NOT gate happens here, you'll realize that the results come out. There's a 50% chance that it is 0, 0, and a 50% chance it is 1, 1. No other result will happen. And this really puts these two qubits in what we call superposition. I'm jumping a bit faster than what I will normally do in a normal quantum program, but it's really what it is. This is how quantum programs are written, and they're all written in gates. And from building onto these gates, you start to do more and more things, and you start to learn about more algorithms, right? So we have this simulator that you can try. It's on our GitHub page. You can just use it and try and use as much as you want. If not, you feel like you like Python programs, you're still free to use Qiskit. There are also other kinds of quantum simulators, from PennyLane to Keyboard Science, and many as well. So go try them, go understand, go play with them. What I want to bring forward is this thing here now. Once you start to understand about quantum programs, then you start to say, hey, let's do things, right? I mean, and as with all new technologies, we always use it for bad things first, unfortunately. This is the very, very sad part of human nature, I don't know. So Shor's algorithm, and this is a circuit. This is a circuit that shows you how to factorize 21. 21, right? Yes. This is a circuit that teaches you how to factorize 21. Actually, you don't need a program to know how to factorize 21. I also know 3 times 7 is 21. But it's just to show you that you can literally write a program. You can literally calculate how often or how soon and how fast, in O notation, the computation complexity in trying to do this, and realize that, hey, to factorize 21, I just need 3 rounds. Oh my God, something is scary. And if you then extrapolate it to what we're looking at, say, RSA 2048, which is a 2048 bit number, what is the number of qubits you need? You start to be able to do that kind of calculations. And so if you want to factorize 21, you can use your brain, and you can use a quantum simulator to do that. And this is one example of what a quantum computer can do. It can break some of the existing problems like factorization, like discrete log, that we think is impossible for a normal computer, even with a GPU, to solve. That's supposed to be something that's supposed to take millions of years to solve, suddenly can be solved in a couple of hours. Starts to get scary. Okay. Another algorithm is Grover's algorithm, which is for brute force search. You can also try it out. And that allows you to be able to search for things in what we call quadratic speedup. Example of what that means, if you are looking at 100 items, what is the chance of finding an item? Okay, sorry, I repeat. If you have 100 items, how many times must you check before you can have a 50% chance of finding this item? If this is unsorted, you need to look for it 50 times, right? Because 100 items, I need to look for it 50 times, and I have a 50% chance of finding this item. Using Grover's algorithm, you don't need to look for it 50 times. You just need square root. I just need to search for it 10 times, and I will find that item. And that is the speed up that a quantum computer can bring. It's not a logarithm speed up that Shor's algorithm do, but it's still a significant speed up. And they're seeing, what can we do with this? We don't know. We'll find out when a quantum computer is around. Okay, so with this kind of possible algorithms that's starting to come out, this is really where the exciting part comes in. the part that one of the reasons why I'm coming here and talking to you guys is that these algorithms were invented by physicists. They were not invented by computer science people. And I think it's time that you guys stepped up and look at what kind of algorithms can be done. If you look at the number of AI algorithms that are invented, maybe within the last 1 week or 1 month, probably about 1,000, 2,000 new algorithms and new models that are being created every week, every month. You know how many quantum algorithms are there from the day they started until now? It's less than 1,000. Okay, you just go to Quantum Algorithm Zoo, you can search for it. But that is all the quantum algorithms that have been invented. And it's a really, really pathetic number inside there. Okay, it's until you guys come in, step in, understand what needs to be done, and really start to invent quantum algorithms that's going to change the world. Okay, so it's coming. Start to look in if creating or designing algorithms is something you're interested in, definitely something that's worth looking into. Okay. Any questions so far? Oh, very quiet there. So no, most people don't program in Gates. Most program in Python. So they use Python code to write, but ultimately in the Python code, you are still coding Gates. So if you go to Qiskit, you're going to see a lot of it is still writing in Python code, but all about programming the gate values inside there.
Like, are there higher level abstractions? For example, don't think of programming as like or that.
And right now, most of the thinking is still at this level because they are still designing algorithms at that level. And in order to say design, so they have higher level abstractions. Like can I call a Shaw's algorithm? Can I call a QAOA algorithm? But underneath it, still Gates. There's nothing higher than that right now. And if you can start to think of it, like, is there a quantum operating system? Don't have. Okay, the most recent announcement. So if you think that this is an area that you want to really try to make money from, 2 weeks ago, last week or the week before, sorry, 2 weeks, 2 weeks ago, Horizon Computing. Horizon Computing is a startup in Singapore. They just announced a spec, a possible MOU spec, valued at $500 million. What do? They are writing a quantum compiler that takes classical code, means basically your programs, takes classical code, recompile them into quantum programs. $500 million. I'm sure you guys can do it in a night, right? I mean, 1 weekend can do already, right? Exciting, or? Huh? Wow. Yes. Horizon Computing. Huh? Interested already? Wow, he also another $500 million. So this is we are really at the cutting edge right now. Every quantum conference that you go to, they will say, we don't have enough quantum software engineers. We don't have enough quantum programmers. We don't have enough people writing new quantum algorithms. No bluff. Okay? So this is really an area that I'm hoping that you guys look into. So anyway, I'm going to switch over to then talk about my startup, about what I'm doing, and where I play a part in this whole thing, right? So a bit of background, I'm a very old man. I went through Y2K. I coded in COBOL. I coded in VEX. I coded in mainframes. Really, I learned COBOL in school. I did COBOL to help companies fix Y2K. Now I'm hoping to help companies fix quantum. That's how old I am, unfortunately. Thankfully, during my journey, I had some fun. We built a lot of code. We delivered security solutions for banks, for governments, and during that time, I also went back to do my PhD. Now I did it at SUTD, and now I'm back running my startup. Startup is only 2.5 years old, doing what we call quantum cybersecurity. If you are graduating within the next 1-2 years and you want to intern with me, come right to me and then we can talk about it. Okay, but anyway, we are doing quantum cybersecurity, so I just jumped to this. So what I said so far, right? So I was first on the SWOT side, right? Someone is building a SWOT to try to attack. Now I'm trying to build the shield to try to defend. That's what it is, right? So we believe that quantum computers are coming in the next 5 years, 5 to 10 years, depending on who you listen to. Google says 5. Jensen Huang originally said 15. Now he's changing his mind. I don't know what he wants, but it's coming. And what is affected? A lot of your systems, mainly cryptography. Using Shor's algorithm, what is affected? Public key cryptography is affected. So if you understand, if you learn cybersecurity, you learn about cryptography, there's asymmetric key cryptography, there's symmetric key, there's hashing, and blah, 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 blah. Asymmetric key cryptography is vulnerable to Shor's algorithm. What is the specific vulnerability? Given a public key, asymmetric keys has a public and private key, right? Correct? Can anyone name an asymmetric key algorithm? Good, RSA. What else? Elliptic curve, ECC. What else? There are 3 standard asymmetric key. Sorry? Well, Algorithmal, but what's before Algorithmal? Huh? No, Diffie-Hellman. Right, so these are the 3. So the 3 standard asymmetric key algorithms that are used literally for your web browsing, for your secure email, for your document signing, for your file transfers, for your blockchain, for your IoT, for your video feeds. RSA, ECC, Diffie-Hellman. These 3 are vulnerable to Shor's algorithm, and we need to replace them. That is what post-quantum cryptography is about, right? We need to replace them. How do you replace them? That's where the fun part comes in. Right? So there are already a lot of industry developments coming up. And it's very real. So NIST, the National Institute of Standards and Technologies in US, came up with the new algorithms to replace them. I'll share a bit more after this, but in August last year, the algorithms have been announced. You can literally go online, open source, take the code, start to compile and run it yourself. The different countries like US, UK, most recently UK, Australia have all announced, hey, by sometime between 2030 to 2035, all these systems need to be upgraded. You guys are going to graduate in a time when we have quantum migration. It's probably going to take up your career for the first 3 to 5 years of your life, because everyone will talk about quantum migration. Just like when I graduate, everyone talk about Y2K. same process. You might have to learn cryptography if you didn't. You might have to learn about networking and all the protocols underneath it if you didn't, because it's all about migration. And it's going to affect every single thing, right? Because from an enterprise standpoint, they literally don't understand it. Most of the people running all the banks, the governments, where did they learn about post-quantum? I don't know what you're talking about. It didn't teach. I wasn't taught in schools. In fact, is anyone taking a post-quantum module in NUS, in NTU? Don't have, right? Learn on your own. Scary. Even if they try to hire someone, I want to hire an engineer with 3 years experience in post-quantum cryptography. Tell me where to find. I don't know where to find. If you started doing post-quantum right now in your undergrad, and when you graduate in 2 years, 1 year, you can say that I have experience. I have 1 year experience in post-quantum cryptography, and that's probably going to be a very valuable thing in your CV, isn't it? Okay, so that's the crazy part of it. And there are already threats happening, right? So let me just jump a bit into the oops, I will show you what it means to the threat here. So I said before, right? Public key or asymmetric key cryptography is affected. you have always when you talk about cryptography, you always talk about Alice and Bob, right? So if you want to show people that you know cryptography, what you say, well, Alice do this, Bob say that, you sound like you know your cryptography or that. Correct. It must be Alice and Bob. Huh? No, no bluff, no bluff. Really, really, I'm not kidding you. You go there and start talking about Alice and Bob, they think you're a very smart person, really. So don't use any other Brian or Bernard or whatever. Alice and Bob. Alice is sending a message to Bob. Alice wants to make sure that the message that she sends to Bob is encrypted so that nobody can look at the message, right? You are talking about confidentiality. So how does that work? Bob gives his public key to Alice. He says, Alice, please encrypt using my public key. Bob says, use the Bob's public key. So Alice takes the message, encrypts it with Bob's public key, sends it over. Bob then uses his private key to decrypt. Nice. This is the basic of asymmetric key cryptography, except that when there is someone called Eve, the eavesdropper. Okay, so bad person is called Eve, not Evelyn, not anything else. Eve. Eve is an eavesdropper. She collects the encrypted data. Okay, she's going to what we call harvest now. Collect this encrypted data and store it. Nowadays storage very cheap. I know Amazon S3 not so cheap. Storage, they store the encrypted data. I go outside, I go to a Wi-Fi, I go to a Starbucks, I just literally collect all this. I just do packet capture. I'm not asking you to do it, please don't do it. I collect all this data and you just keep it first. Because in 5 years' time, when a quantum computer is available, Eve is going to take Bob's public key, calculate Bob's private key, decrypt the data, and look at it. That's what they call the harvest now, decrypt data. Okay, so this is a real threat that happens today, right? Is there something that you are doing today through your communications that you cannot accept it being displayed 5 years later? If there is something that is in that category, then there is a little risk that you are taking. Is someone targeting you? Is there an Eve that's targeting you? Maybe not, but who knows? I'm sure that Eve is targeting the military, the government, and some of the bigger enterprises. And that's what they are afraid of, because it needs to be fixed today. If you don't fix this today, in 5 years' time, if your health records start to be seen, if your tax records, maybe for you guys make a lot of money, so need to pay tax and pay a lot of tax. But if these records start to be shown, then it's not so nice, right? And this is the threat that we literally have to fix today. And this is what we are working on. We, as in my startup, is working on to help organizations upgrade and fix these kinds of things. Okay, so understand? Any questions? No? And definitely what we do then is about post-quantum cryptography. So example of what we have done, we call it safeguard web pages, where we literally implement the NIST post-quantum algorithms in order to encrypt data on top of your SSL session, because your TLS session is not safe. We encrypt on top of that to do the post-quantum encryption. So again, Alice and Bob, right? Doing the transmission and that the transaction is not secure. So we have a JavaScript implementation in the browser. We have a HSM or hardware security module in the backend. And we do the same thing. We are still doing public key encryption, but now using MLKEM, which is a new standard from NIST that encrypts data on the browser using the public key of the server. And the server then decrypts the data in order to have onward processing. And if who tries to collect any of this data in between cannot decrypt it, because it's using a new generation of cryptography called post-quantum cryptography that we know is not susceptible to Shor's algorithm. That's it. Not very difficult, right? You're very quiet. Question? Anyone? Unfortunately, I don't have stickers, so I don't have anything to give. But anyone? Any questions? No. Yes. Or like Chrome at least, I thought now they have like advantage of MLKEM. Well, they have a certain version, so it depends on the web server. It's between the web server and client, right? So you are right that some of the TLS implementations are already what we call a hybrid encryption. So they are supporting both the 25519 as well as MLKEM inside the browser. But that is what we call point-to-point encryption, because from the web browser, data goes to your CDN, right? Your content delivery network, your content delivery guy, who is your Cloudflare. So between the web browser to Cloudflare is encrypted. And then Cloudflare opens another session to the enterprise. That part is encrypted. Within Cloudflare, not encrypted. Understand? Correct, right? Because ultimately we have a browser. You have a PC that goes into your browser with a CDN here, and then it goes into your enterprise, right? Okay, right. And this guy is another web server. Between here to here, web server here, web browser, you have your TLS, and then here to here, another TLS. TLS stands for Transport Layer Security, right? So this is another is a web client to your web server. But what we call point-to-point encryption, because here, between these 2 points, data is decrypted and re-encrypted. So technically, Cloudflare can then be the #1 eavesdropper in the world, right? I mean, I don't say that they're doing it, but this is what organizations here are a little wary about, because I may have now data exposed at some point of time. And this is not just one, there may be multiple hops and multiple proxies along the way. So they want data to be fully encrypted. That means that I want data that is encrypted here and only ends here. It should never be decrypted anywhere along the way. And this is why that's why they insist on things like end-to-end encryption. Thanks for your question. Any other question?
Like symmetric key. How are the symmetric key encryption algorithms affected?
How are they?
How
How they are affected? So symmetric key algorithms are not vulnerable to Shor's algorithm, but because there's really not much of a mathematical basis behind it, but they are still vulnerable to what we call Grover's algorithm. Remember, I talked about Grover's algorithm being able to do a brute force search, right? So if I have a key space of, if I have a key space of, if I have a key space of this much, Grover's algorithm is able to do a speed up, right? So speed up to such that now I only need to search for this amount of time, and I can then potentially find this whole thing. So how do we then improve on this? We have to essentially increase the size of the keys. So the standard symmetric key algorithm, what's the most commonly used symmetric key algorithm?
AES.
AES, wonderful. Y'all never do, okay, y'all got learn DES, triple DES. What is DES? What's triple DES? That's my time, unfortunately. So, so we were done migrations from DES to triple DES to AES. We've done migrations from MD5 to SHA-1 to SHA-256. So old people like me have done a lot of cryptographic migrations already. But AES, what's the key size for AES?
128.
Yes. So when we say key size AES 128, it's not that when it says 128 bit, right? The key space is actually 2 to the power 128. Correct? And if you're talking about AES 256, the key space is 2 to the power 256. If you do a square root, if I apply Grover's algorithm and I square root this guy, it goes back to here. So the idea here now is, please, I mean, we're not saying that AES-128 is bad. It's just that it's a lower level of security because someone using Grover's algorithm has a higher chance of finding it because this guy, if you square root, becomes 2 power 64. Oh, so nice. 2 power 64 starts to sound a little small, right? Because dash is also 2 power 64. Wait, dash is 2 power 56, but okay, 2 power 64 sounds a bit small. So most people are saying, please don't use AES-128. Please migrate from AES-128 to AES-256. And once it's AES-256, even you square root it with Grover's algorithm, we're still safe. So symmetric key algorithms are what we call not vulnerable to quantum, but weakened by quantum, right? It's not vulnerable, but we just have to take note of the key size. Does that answer your question? Yeah. Right. Okay. Anything else? Go ahead. Never mind. Let's go on. So another of our implementations is using what we call quantum key distribution, or QKD. So there are two fields that you will start to be exposed to. One is post-quantum cryptography, which is essentially new algorithms that replace RSA, ECC, Diffie-Hellman. And these new algorithms are done in software or whatever. There is also the other one, which is QKD, quantum key distribution, which uses the quantum properties of communication, quantum photonics, to be able to get two keys, same keys in two different locations. So we call distributed in two locations, right? So we have Alice and Bob. I know I didn't draw it properly, but they are Alice and Bob, huh? No other people again. I'm supposed to have a key that is on two sides. And this key must be the same because I want to use AES to encrypt the data. AES is a symmetric key algorithm, which means that I need the same key between Alice and Bob. How do I do that? I now use QKD to distribute this key so that Alice and Bob can use the key to do AES encryption. That's really what the principle is. This goes down into a bit more hardware because now you need this quantum key distribution, which is a connection. So they literally are laying fiber between point to point in order for this quantum communication to take place, and then for this whole implementation of the key to be distributed. And this does then allows Alice and Bob to have a common key to do the symmetric key encryption. And because we're just using QKD and AES, we're not using any symmetric key algorithm, we are not vulnerable to quantum computers. That's really the principle behind it, right? How to implement, how to get QKD working? There are some doing fiber, there's some doing satellite. These are the new developments and technologies that will come in. And where my startup comes in is the key management layer in order to then do all the distribution stuff. So that's part of what we're doing. Because it's not so trivial. It's not like just get two fiber cables and it works. That's a lot more physics. There's a lot more physics to it. You want to learn about it, you have to go to CQT. They have certain QKD networks that you can try it out and you can start to program in it. Okay. That's about a lot of what that's about all that I'm trying to do. I guess this is my last slide, and this is what we're expecting people to be developing today. So a lot of what the push from the industry are based on three areas. One, what we call discovering the gaps. Before I know what is vulnerable, before I know how to fix the vulnerability, I need to know what is vulnerable. So there's a lot of areas in scanning, code scanning, right? Looking at binaries, looking at network protocols, looking at your PCAP files, looking at your source codes, and identifying where are the areas where asymmetric key algorithms are used, key sizes of less than 256 is being used, algorithms that are not quantum safe. So many of these, including Algamal, where are they being used? We have to find them You have to then prioritize them because there's so many of them, and then slowly try to fix them, discovering the gaps, trying to find where the problems are. This is one big area. The second area then is about really fixing the problem, right? Encrypting the data, encrypting it with post-quantum cryptography, using QKD. And the third area is about education. Because before this, I don't know how many people learn about quantum, but if you go out there and ask anyone about quantum, chances are they don't know what's happening. Chances are they don't even want to hear about what's happening because they say, oh, quantum, too complicated, don't tell me. And there is going to be a huge industry just trying to teach people and explain what quantum is. Right? I'm sure that there'll be people starting to do YouTube videos and TikTok videos just to explain about quantum. And maybe they make a lot of money from there. And then all the other awareness. So this covers the consumer side, your healthcare, your enterprises, your banking, your government. A lot of areas that needs to be done. And even after you have upgraded Singapore, there is still the rest of ASEAN that needs to be done. There's still the rest of the world that needs to be done. There's still so many systems that need to be done and a lot of potential new opportunities that we are seeing in this area. And that's why my startup is working on something like this. Okay, so that's about a simple overview of what we're doing. I got 3-4 minutes left. If you've got any other questions, happy to take them. Yeah.
You mentioned that you have to transmit by laying actual cables between the two points.
Yeah.
What happens if it's between two different countries that are connected over so that's one, and then the other one is so who's responsible for laying? Is it like a telco provider? Or is it under you guys? Or is it
So let me answer it this way. So when it's cross-country boundaries, this is where what we call terrestrial QKD has a problem because it is not just about physically laying the line. Bear in mind that in QKD, it's dark fiber and there cannot be repeaters because the repeaters essentially break having a repeater is like sampling, right? Remember I told you, you sample the state, the superposition gone, right? So sampling causes a problem. So you need to have a continuous fiber there. Across the country is a problem, definitely. And in this case here, there is no commercial solution now. They're all in trials where they're using satellite. So they're using a satellite up-down. The only country that has done that is China. So if you read last week, China just announced that they did satellite QKD, China to South Africa. Wow. Miles ahead of a lot of people. Okay, so that's satellite QKD, or then go through a more classical way of doing, which is what we call PQC, so post-quantum cryptography. So my startup, we are working on a suite, like a virtual QKD, which uses post-quantum cryptography to solve that. Your second question is, sorry,
basically
who's doing it?
So
if you are interested in that area, you can go to nqsn.sg. The national NQSN stands for National Quantum Safe Network. So the IMDA has commissioned 2 telcos, Singtel and SPTel, to essentially start to push for this whole NQSN Plus network. And the telcos are the ones that actually are responsible for laying those lines and providing this as a service. So we have two telcos. I mean, if you have ambition, maybe you can be the third telco. Why not, right? I mean, hey, think bigger, come on. Yes.
Yes, you mentioned about educating and everything.
Yeah.
I was wondering, what's the prerequisite knowledge? No, I mean, you say here cryptography and quantum and everything.
Yeah.
What exactly are the prerequisite knowledge that need to attain?
So there is actually not much certification. So if you go, you can literally go online and try to get an IBM certified Qiskit programmer and a few other things. There are not many of these formal education requirements that fall into place for this. Okay, to be frank, you literally can learn on your own, work on it on your own, and come out and be that expert. Unfortunately, the world doesn't think that way. So one of the most common prerequisites for you to do quantum is if you have a PhD in your name. I discovered it by luck because I got a PhD, and then I realized how come people talk to me, they don't talk to the guy beside me, although the guy beside me is smarter than me. because I got a PhD. So that unfortunately delays. Yeah.
What's the knowledge?
You can literally learn about quantum online and discern through it, go through the things. I mentioned that if you're keen about post quantum cryptography, there's this OQS, Open Quantum Safe.org. Go to this guy. This is maintained by the University of Waterloo, Canada. Good guys. They have built reference implementations of the post-quantum algorithms that are standardized by NIST. So if you want to start doing post-quantum algorithms and post-quantum encryption, say that because you have two girlfriends and you want, I'm not sure which one you want to send, and you want to encrypt your messages for these two girlfriends using two different keys, please, you can use the algorithm libraries here. One warning, the code is in C. I think they recently ported some to Rust, but don't have Python, don't have JavaScript, don't have all these things. So you have to go figure it out. I'm sure C is no problem for you guys.
Actually, I think there's a Python wrapper. It's a wrapper.
Rapper lah, fake one lah. Real people write in C, yeah. So I don't know how many people hate me after this. Because actually I only know how to code in C. I don't know how to code anything else.
Well, I see that your startup has a product called Established.
Yeah.
Targeting Bitcoin and ETH.
Yeah.
May I ask what's that about?
That's an experiment that we were trying to do lah, because we know that blockchains also use a lot of post-quantum, use a lot of cryptography, and literally the communication between the wallet to the node is using a vulnerable elliptic curve cryptography algorithm. So it's using ECDSA, and that is going to be a big problem. During my PhD, I did manage to discover an algorithm that can make ECDSA quantum safe. And we were trying to use that to deploy for blockchains and trying to get it there. But the devil is in the details, and the execution is harder than we think. So when we tried to push it in the blockchain world, we're slowly trying to get that algorithm introduced, because it's not one of the NIST algorithms. Right, so if you were following through the NIST algorithms, which started in 2016 and just got announced in 2024, there were originally 70 over algorithms that got whittled down to now three algorithms that have been standardized. Two are in the standardization process, means there are 5 algorithms left. Unfortunately, the algorithm that I worked on is not one of the 5. It's still secure, but it's not one of the 5, and therefore you'll start to realize that industry is not so forgiving, right? I mean, they may look at it and say, yeah, it's secure, but because it's not standardized, I don't want to use it. So we built that product out, but we realized that we couldn't move forward with that product. Not at the moment. Hopefully things will work out.
Sorry,
Yeah.
you make ECDSA.
Yeah.
Are you referring to NTRU or is there another keyword?
No, NTRU is still a lattice-based system, right? So lattice-based. What is the problem with? Okay, can I take up a bit more time? Okay. So keys. Okay, so wallet, blockchain. All you trade Ethereum blockchain, right? All you very rich one, right? So you have your wallet and you have your blockchain. Correct? Huh? Right. And between your wallet has a private key. Your on the chain is your wallet address, right? What's your wallet address? How does your wallet address work out? How does it work?
Public key.
Yes, hash from the public key, right? So there is a public key. And if you hash the public key, you get your wallet address. Okay, so this is the basic principle behind it. This implementation is based on ECDSA SECP256K1. Okay, that's the specific algorithm underneath it. So that itself is not quantum safe, because now, so let's be very accurate. If you have a wallet that you never spend money because you're super rich, you don't need the coins, all the coins only come into your address. You have never shown your public key anywhere. You have never done a transaction. Then quantum safe, right? Because as long as your public key is not exposed and your wallet is exposed, your address is exposed, from a public key, hash or public key, go back public key, cannot what? Can only use Grover's algorithm, right? And this one, and say for Ethereum is based on catch up 32, for Bitcoin is based on right 160 plus SHA-256, cannot one. So this part is not vulnerable. But if you need to spend, the day you spend, it goes into a mempool, someone take the quantum computer, front run in front of you, gone. All your coins gone. So you can only see in the wallet but cannot spend. Correct. So anyway, this is thing. So that's more accurate. But in general, most of the coins in all the wallets that have been spent a little bit, right? So the public key is exposed. Therefore, given the public key, Mr. Hacker will calculate the private key, then spend all your money. Gone already, right? So this is a vulnerability, right? Because from public key, I can calculate the private key, right? This is the quantum. So how to fix this? If you use any new algorithm, you use MLDSA, you use SLHDSA, you use any of the new NIST algorithms, private key is there. Even if you keep the same private key, what happens is that your public key becomes a different public key because of the new algorithm. And if your public key is different, your wallet address is different. That means that if we are going to implement a new post-quantum algorithm in Bitcoin, in Ethereum, all 100 million wallet addresses need to change. Everyone will say, all of you, please move from this wallet to that wallet. Who will win? Tell me. The scammer, right? I tell you to click this button. One out of only 99 of 100 times you click that button, your coins will be flushed, gone already, right? Sure, right? that's the most unfortunate thing, because you're trying to convince 100 million people to migrate their wallets, Wow. If you can do that, you are Vitalik number 2, because I cannot imagine anyone who can do something like this. Maybe he can, but cannot. There is no Vitalik in Bitcoin. There's no Vitalik in all the other coins. How to move? So, unfortunately, a lot of the public chains are stuck on this ECDSA. So let me share with you a bit of my PhD, what I did. We start from the principle of hashing again, right? Seed phrase. Right? I mean, you start with a seed. Most people don't remember. Do you remember a private key? Don't, right? You have your seed phrase, right? A seed phrase is a set of words that essentially hash to the private key. And we know that hashing is not vulnerable. So if we provide a zero knowledge proof with every transaction, so every time you sign something, I provide a zero knowledge proof that I know the seed phrase, then life is good. I literally don't have to migrate anymore. So this was one of my papers that I did in my PhD. So we were using this, the algorithm we were using was Picnic. So Picnic was one of the round 3 algorithms. I fell in love, I studied it, I fell in love with it. Wow, I did my whole PhD in it. And I tell you, this is lucky, right? Because I did my defense in June 2022. I did my defense in June 2022, and I showed this algorithm, then okay, pass. In July 2022, they say Picnic not inside the list anymore. Imagine that if I would then have to ask the question, if this algorithm so good, why is it not inside the list? But anyway, that's a joke. So I got lucky. I managed to do my defense before the announcement of the selection happened. So this was part of my PhD. And so we filed a patent on it, and we're trying to commercialize it. Sorry, yeah.
Maybe that's the last question. If there's no seed phrase, then we're out of luck, right?
Okay lah. I mean, I cannot solve everything lah, but yes, you are right. I don't have an answer for you.